You know, right now, all around you, there's this invisible ocean of information. It's literally in the air, it's in the walls, it's in the device you're holding. In this explainer, we're going to pull back the curtain on that invisible world. We're going to see how we take all that chaos and turn it into order.
So let me ask you something. What could the sound of your own voice possibly have in common with your Wi-Fi network? I mean, it's a weird question, right? But believe it or not, they share a fundamental identity. The answer is pretty simple. They're both signal.
And really, that's all a signal is at its core. It's just information in motion. Think about it. The vibration from your vocal cords creating sound waves, or the radio waves carrying data to your laptop, it's all just some value, could be pressure, could be voltage, anything really, that's changing over time to mean something.
But a raw signal on its own, it's just noise until we can actually make sense of it. And that's where signal processing comes in. This is our universal translator. It's the set of tools we use to read, to clean up, and to understand what all these signals are trying to tell us. It's literally how your phone turns invisible waves into your friend's voice.
Okay, so to start making sense of these signals, we first have to understand the two fundamental kingdoms they belong to. And this, right here, is probably the most important distinction in the entire world of signals: analog versus digital.
The difference really comes down to smoothness versus steps. An analog signal is perfectly continuous. Imagine a ramp where you could stand at any possible height, down to the tiniest fraction of an inch. That's analog. A digital signal, though, that's more like a staircase, or maybe a ramp built out of Legos. You can only be on one specific step, never in between.
So if the real world is analog, how do we get to our super useful digital world? Well, it's a two-step dance. First, we do something called sampling. It's like taking a series of snapshots of the analog signal at these tiny, regular intervals. Then we quantize it. For every single snapshot, we round its value off to the nearest approved Lego brick height. Yeah, we lose a tiny, tiny bit of perfect detail, but what we gain in return is absolutely massive.
But why? Why go to all that trouble? Well, because digital signals, with their simple, predefined steps, are incredibly tough. A little bit of electronic noise, a little bit of heat, it's not going to accidentally turn a step 5 into a step 6. In the analog world, though, any tiny interference changes the signal. Digital is just more robust.
And this chart really lays out the trade-offs. Sure, analog processing can be blazing fast in some cases, but digital just dominates when it comes to flexibility and performance. You can completely reprogram a digital system just with software. It's adaptable, it's powerful, and that flexibility right there is the engine that drove the entire digital revolution.
Okay, so we've got analog and digital down. Now we're going to go a little deeper. I want you to think of yourself as a kind of naturalist. We're going to head out into the wild and learn how to identify all the different species of signals you might run into.
And here's our spotter's guide. This is what we'll be looking for. We're going to classify signals based on 5 key things: how they behave over time, whether we can predict them, if they repeat, what their lifespan is like, and when they start. So let's get into it.
Our first stop is all about time. A continuous time signal exists at every single moment. It's like a movie. A discrete time signal, on the other hand, only exists at very specific separate points in time, kind of like a flipbook. And hey, remember that sampling step we just talked about? That's exactly how we create a discrete time signal.
Okay, so we know how a signal exists in time, but can we predict what it's going to do? This leads to our next classification. A deterministic signal is one we can map out perfectly with math, like a pure musical note from a synthesizer. A random signal, though, is unpredictable. Think of the hiss from radio static. We can describe its average behavior, sure, but we can never know its exact value at any given moment. Now, this next one is hugely important. Repetition. A periodic signal repeats the exact same pattern over and over and over again. Think about the 60 Hz cycle of AC power humming in your wall, or the carrier wave for an FM radio station. Aperiodic signals, on the other hand, are one-offs, like a single clap of thunder. They happen, and then they're done. And you know, there's this beautifully simple mathematical rule for it. It just says that the signal's value at any time t is exactly the same as its value one full period, that's the t0, later.
This one little law governs everything from radio waves to the rhythm of a heartbeat.
And this whole idea of repetition connects directly to a signal's lifespan. An energy signal is time-limited. It contains a finite burst of energy, like a flash of lightning. A power signal, however, goes on forever. It has infinite total energy, but a finite average power. It's like the sun, it's just always on. This is why most of those repeating, periodic signals we talked about are considered power signals.
And finally, the start time. A causal signal is one that is zero until, well, time zero. It doesn't exist before it starts. This might sound a little abstract, but it's absolutely vital, because every single real-world system we build is causal. It can only react to something that has already happened. We can't build a system that responds to an input from the future, at least not yet.
So, we've taken quite a journey, haven't we? We've gone from this huge, confusing world of invisible information and learned how to sort it into a structured, ordered system. But why? Why does all this classification actually matter?
It matters because you can't build a filter for radio static using the same design you'd use for a Wi-Fi decoder. It just wouldn't work. By classifying signals, we can design specific, incredibly efficient systems to handle them. This isn't just some academic exercise. It is the fundamental blueprint for pretty much all modern communication and technology.
And that brings us right back around to why the digital approach pretty much took over the world. It's that ability to reconfigure systems with software. That's the flexibility. And to do it with amazing accuracy, all at a reasonable cost. That's what gave us the power to build the complex, signal-driven world we all live in today.
So let's just boil it down to the absolute essentials. First, signals are just data that change over time. Simple. Second, our digital world is literally built by taking snapshots and rounding off the analog world around us. And most importantly, classifying all these signals isn't just for fun, it's how we learn to speak the language of modern tech.
Which leaves us with one final thought to chew on. We have gained so much from this digital revolution. Reliability, power, incredible flexibility. But in that process, in rounding off the universe into all those neat little steps, what richness, what subtle nuance from the original analog world might we be leaving behind? Something to think about.